Alright guys, as promised, a precursor to the notes that we're going to take on Monday. I am going to skip a lot of the algebra that I did between steps on this video, just to save space and time. I do recommend that after you take notes on the video itself, that you do go back and practice the algebra that I skipped over. So we're going to start out with an example using the Riemann sum first and then using the definite integral second. In this example, we're going to find the area made by f of x equals 2x and the x-axis between x equals -2 all the way to x equals 0. To start off, I'm going to draw a picture of my function so that I have an idea of the area that I'm actually trying to find. As you can tell, I could do this with a triangular formula, but we're going to do it with the sums instead. For my delta x, because of the proof that we did in class, I'm only going to use the lower limit, the lower sum for my delta x, because we know that after we take the limit, the lower sum and the higher sum will both end up being the same value. And of course, using my lower sum, the delta x is equal to -2 plus 2i over n. And the I is from the summation formula. The n is from the number of rectangles. So setting up my Riemann sum and going ahead and adding the limit, since I'm going to skip the algebra for it anyways, the limit as n goes to infinity of the sum from I equals 1 to I equals n of f of x, which in this case is 2 times my x substituted in, times my delta x. Now, after several steps of algebra, and this one took me, I believe, 4 lines of algebra, and using the shortcut values from the previous chapter, I get that I have a limit as n goes to infinity of -4 plus 4 over n. So this is after using the substitutions from the area chapter that we just finished. And of course, if n goes to infinity, the 4 over n goes to a value extremely close to 0 that I can call 0, and I'm left with just a -4. Now, there is another way that I can find the same value, and it's called a definite integral. And it uses the antiderivatives that we did a couple of weeks ago. So here it is. I'm going to start with my indefinite integral symbol, but this time I'm going to label from -2 to 0, from on, bottom, and top. I'm going to take the antiderivative of my function, then I'm going to substitute final minus initial values into my antiderivative, and I end up with -4, same as using the limit definition for the Riemann sum. Now, this symbol right here, the straight line, that means that I've already taken the antiderivative of the function, but I'm still using that line to represent that I'm going from -2 to 0 as my x values. So once again, no matter if I use the limit definition of the Riemann sum or if I use this definite integral, I still end up with the same value. In the second example, we need to find the area under f of x equals 4x minus x squared, going from x equals 0 to x equals 4. Again, I'm going to draw a picture of my function in the shaded area I want to find, and this is just to help me figure out what my delta x and my x need to be. My delta x is going to be the 4 divided by the number of rectangles that I want, and again I'm only going to use one of the x values, because once I use the limit it should be the same whether I use the upper sum or the lower sum. Writing my Riemann sum with the limit definition, I have limit as n goes to infinity of the sum from I equals 1 to I equals n. and this is of f of x with my new x substituted into the original function, times my delta x. And then after several lines of algebra, this one took me about 8 lines of algebra, I get the limit as n goes to infinity of 32 over 3 times 1 minus 1 over n squared. Now, as n squared goes to infinity, that second term goes to 0, and I'm left with 32 over 3 times 1, which is 32 over 3. Now, using the same definite integral technique that uses the antiderivative from the last example, I'm going to write my integral symbol, going to make a notation that I'm going from 0 to 4. I write my original function, don't forget the dx, and then I'm going to take the antiderivative of my original function. Write my straight line, and again, note the boundaries, 0 to 4. I'm going to plug in the value of 4 first into my antiderivative, and then I'm going to plug in the value of 0 into my antiderivative. Now this gives me a total of 32 over 3, which if you notice is the exact same as what we got from the value. From the limit definition of Riemann sum. So in conclusion, you can find the exact area of a function between the function and the x-axis by using limits and the Riemann sum, or you can also find the exact area of a function between the function and the x-axis by using an antiderivative and giving it initial and final limits. That's all for this video. Thank you for paying attention. Go back over your notes and fill in those missing steps of algebra. You need to practice that so that your solutions for your homework become a lot faster. See you on Monday.